All right, so my final story will be about this new satellite, TESS, or the Transiting Exoplanet Survey Satellite, that was launched just the other week. And this is the United States' next effort in having a space observatory that can look for and discover new planets around other stars. And so the real workhorse over the last 10 years has been the Kepler satellite. And for those of you who've been coming to 60 Minutes in Space, you've heard lots of news stories involving Kepler discoveries. But what is special about, or what's unique about Kepler is that it basically points in one direction in the sky towards the constellation of Cygnus. And so this, the galactic center is actually off in that direction again, and are actually over here. And the Laguna Nebula that we saw earlier is just over here. So the Kepler points away from the galactic center towards the constellation of Cygnus. And during the last couple years, the reaction wheels on Kepler failed to the point where it couldn't keep pointing in that direction. And so Kepler has a new mission where it actually images along the plane of the Earth's orbit. But most of our discoveries about planets in other outside of our solar system have been along basically this beam that what Kepler was looking at. So currently, I think on the order of 3,000 planets, over 3,000 planets have been discovered by the Kepler satellite. Well, the difference between Kepler and TESS is that TESS will be focused not just in one direction, but it will be looking at all directions in the sky. But because it won't be staring at that at the same patch of sky for a really lengthy length of time, it will only be able to see some of the brighter stars. But that's really important because there are lots of bright stars that are close to our solar system that would actually be easier to investigate. So a lot of these Kepler stars that have planets, the stars and the planets might be 1,000 or a couple thousand light years away. And because they're so far away, it's really hard to investigate the nature of those planets, what their atmospheres are made up of, for instance. Whereas if we can find lots of planets that are close to the sun, we can use ground-based observatories as well as future and current space-based telescopes to learn more about those planets. So next, we're going to just watch some videos.
8, 7, 6, 5,
the Kepler,
4,
or the TESS
3,
satellite
2,
was launched with a SpaceX Falcon 9 rocket.
Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
SpaceX ascent commentary. Once again, we'll make call-outs on the trajectory of the rocket. Status of stage 1.
Stage 1 propulsion nominal.
The SpaceX Falcon 9 has begun the pitch kick maneuver.
All right, and then I have another video from NASA that actually talks about how TESS will actually work.
TESS will search for these new worlds, or exoplanets, using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TESS can detect those subtle dips and even use them to determine some basic features of the planets, such as their size and orbit. Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a vertical strip of the sky called an observation sector.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all the bright nearby stars.
TESS will watch each observation sector for about 27 days, before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky. This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS will fly in a highly elliptical orbit that maximizes the amount of sky the spacecraft can image and is carefully timed with the orbit of the Moon. It will spend most of each 13.7-day orbit collecting data, and then, as it passes closer to Earth, it will transmit that data to the ground. Because TESS's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the two missions to work together to first find and then carefully study exoplanets. Since most of the exoplanets found by TESS will orbit bright stars, missions like Webb will be able to measure the spectra of starlight absorbed by the planet's atmospheres, which can indicate what they're made of. Ground-based measurements of the TESS exoplanets can determine their masses. Combining the masses with TESS's size measurements reveals densities, allowing scientists to better understand the exoplanets' compositions.
So, as we saw, TESS is going to cover the entire sky and at different degrees of depth. So, as we saw, there's going to be a big overlap near the poles. And here, these colors basically tell you how many days worth of observing are being focused on at each of these different patches. So the blue is only 27 days worth. So that means that if you're looking for planets around another star and you're trying to find those transits, you'd be able to see transits or confirm a transit as long as the planet was orbiting less than, on the order of no more than a few weeks around each star, because you want at least 2 or 3 transits to confirm the existence of a planet. And but as you get closer and closer to that cap, up near the top here in the red, you're getting close to 350 days worth of measurements. So we're definitely they're definitely interested in getting lots of targets that can be further explored with the James Webb Space Telescope. Now, how big are the areas that they're covering? Here is a degree patch in the sky, and this is actually pretty big because you could fit 4 full moons in a degree square patch. So that same degree patch is that little green square here, and so this is one CCD or one detector from the main instrument, which is about 12 degrees across. And what they actually do is they put 4 of these together in each of the cameras. And so each of those cameras covers about 24 degrees, and then there are 4 of them, as we saw, that range that covered about 90 degrees up and down. And 24 degrees is pretty big. This is the Orion constellation. You can see you can more or less include most of Orion within a 24 degree patch of sky. So these cameras are really are observing a big part of the sky all at once, about 27 days at a time. Now, it turns out that there are different modes that the camera actually runs through. So it is constantly taking data, but it doesn't necessarily send the data back down, or doesn't necessarily save it. So every 2 seconds, it takes a snapshot, and those are basically used to make sure that the telescope is locked on and not moving from the points in the sky that it's supposed to be looking at. So those are done every 2 seconds, and then every 20 seconds it does save out data from about around 1,000 stars, and there are astronomers who are interested in learning about star quakes, and in order to do that you have to be able to get data relatively quickly, or be able to take lots of snapshots from those stars. So that's one experiment that TESS will be doing. And as far as looking for planets, what it'll do is it has a list of about 200,000 stars that astronomers are interested in. These are known stars that are within that 200 light year radius. And so these are stars that people have, realize could be really interesting to have further study of. And so every 2 minutes, TESS will send back or save information for those 200,000 stars. And finally, every 30 minutes, TESS will save out the entire frame, what it calls the full field images. And those are basically the entire patch of sky that each of the cameras are looking at. So here is kind of the sky all flattened out, and in red are the 200,000 stars that have been pre-selected, and so these are the ones that are of particular interest, and they're going to be looking, making observations every 20 seconds, or not 20 seconds, 2 minutes between observations. And then in blue are other stars that can be picked up in the full field images. So whenever TESS does the full download, and it's estimated that they could observe on the order of 20 million other stars in those full field images. And so how many planets you can actually detect, we'll see what that number is in just a minute. But this diagram shows how many stars you'd expect from TESS. So those are the red stars here. And then here are the Kepler stars. And what we've plotted is how bright the stars are. So the brighter the stars are, the further up towards the top they are. And so you can see that many of the TESS targets are naked eye stars. Many of them, or a vast majority of them, can probably be seen with binoculars. And then there's some that can only be seen by telescopes. And then because Kepler was staring just a sort of a pencil beam out through space, many of the Kepler stars are much, much dimmer, although some of them can be seen with binoculars and telescopes. You can see some of those here. And then also plotted on here is the size of the planet that they're expecting TESS would be able to see, as well as the ones that have been detected by Kepler. And so here, this one represents a planet that's the same diameter as the Earth, and then this is the same diameter as, or 10 Earths. And let's see, this is logarithmic, so 4 would be somewhere around here. A Neptune-sized planet would be roughly about here, and a Jupiter-sized planet would be roughly about here. So TESS would definitely be able to see planets down to the Earth as well as Jupiter-sized worlds. But there's also a big middle here of planets that are bigger than the Earth and smaller than Neptune. And we don't have any planets in our solar system that are in between the Earth and Neptune in size. But it turns out that out in the rest of the universe, the majority of the planets that have been discovered by Kepler turn out to be either super-Earths or sub-Neptunes. So we'll be able to investigate those worlds or find more of those. And finally, it's thought that one estimate is that from those 200,000 pre-selected stars, you might find 5,000 stars that are definitely worth looking at. And so they will be targets of Earth-based telescopes, and they'll be used to get better measurements of the stars so that we can figure out what the masses of these planets are. And perhaps 100 of those stars will have small enough planets that we can do super high resolution measurements with super sensitive instruments, and we'll be able to have at least several dozen planets with really well measured masses. And just released this past week was a paper, again appearing on one of these paper servers, where they did a much more better estimate of how many planets you might expect to find. And so they estimate they'll get on the order of 800 planets from those 200,000 stars. So using the 2-minute observations, and then the full field frames might give you another 2,700 worlds as well. So we'll be seeing, with TESS, we could easily double the number of planets that are known from what was discovered by Kepler. And then finally, also in this paper is an estimate of all the current worlds that have been discovered using ground-based telescopes. These blue circles are ones that have been discovered by Kepler, and then from their model, these astronomers plot in orange the the planets that are discovered through TESS. And so this tells you, again, this is on the order of a couple hundred, or about 300 light years here. So most of the TESS planets will be relatively close by, but again, you'll be discovering objects that are Earth-size all the way up to Neptune-sized worlds.